So far, we've discussed what it means to integrate a function over a region in the plane, but we haven't yet said how to actually evaluate such an integral. So now we're going to learn how to actually compute an integral in the case where the region that we're integrating over is a rectangle. In that special case, we're going to learn how to actually evaluate a double integral. And the main idea is shown in this picture here. So remember, geometrically, if f is a function of two variables, x and y, and we want to integrate f over this rectangle R in the plane, geometrically what we're doing is we're computing the volume of this region under the graph of f. We're computing the volume of that 3D region. And how can we actually compute that volume? Well, here's one way to look at it. Take this three-dimensional region under the graph of f and chop it up into slices. So here you see this purple slice, that's one slice. And you can imagine the whole 3D region can be chopped up into slices like this. And now let's compute the volume of each slice. So how do we get the volume of a slice? Well, we have to take the area, which here it's the area of this slice is called A of x. And then we have to multiply that area by the width of the slice. So it's like area of the base times the height. If we take A of x and multiply it by the width of this slice, then we get the volume of this slice. And then we just add up all those individual volumes. Let's see how this works in more detail. I've attempted to reproduce that picture here. And we want to compute, if you can still visualize this, we want to compute the volume of the region under the graph of f. We're chopping that region up into slices. Here's one slice. And we want to compute the volume of this slice. So the volume of this slice is equal to the area of this surface of the slice multiplied by the width of the slice, which I'm going to call delta x. That's the width of one slice. And so this surface area times this width gives us the volume of this particular slice. And this is the ith slice. So now we just have to sum up the volumes of all the individual slices. Here I can go from 0 up to n minus 1. And we have just added up the volumes of all these slices, and that gives us the total volume of the region under the surface, at least to a good approximation. So this is approximately the volume of the region under the surface. But let's look more closely at this sum here. If you might notice, this sum actually looks just like a Riemann sum from single variable calculus. And this Riemann sum is a Riemann sum that approximates the integral from a to b of a of x dx. So our goal was to compute the volume of the region under the graph of f. And what we discovered is that this volume is equal to the integral from a to b of a of x dx, where a is a function that tells us this area, the area of this slice, which is located at x. Okay, but how do we compute a of x? Well, how do we compute this area, the area of this face of the slice? Well, that's just a problem from single variable calculus. This, from just using single variable calculus, a of x is equal, can be computed as itself an integral, and it's the integral from c to d of f of x, y, dy. In single variable calculus, we compute an area by doing an integral just like this. Keep in mind, think of x as held fixed, and then we're integrating with respect to y. So putting these pieces together, what we discover when we put these pieces together is that the volume of the region under the surface, in other words, the integral over r of f of x, y, dA, this is equal to the integral from a to b of a of x dx, but a of x is given by this integral. So we have integral from c to d of f of x, y, dy, and then dx. So what I did there is I took this a of x here and I replaced it with this expression for a of x, and then I came up with this final formula for the integral of f, the double integral of f over the region R. It's been, this double integral has now been expressed according to this formula. And we can use this formula to actually evaluate integral